The standard machine learning-based seismic interpretation pipeline relies on using prior or synthetic data to pre-train a model and then adapt this model via fine-tuning or some other domain transfer technique to the target data from a new site. The adapted model is then assessed both quantitatively and qualitatively to guide decision-making. The problem is there is still several open challenges in this pipeline. The first corresponds to the nature of the data itself, namely how different the source and target domains are. The second corresponds to the strategies used for domain transfer between the source and the target, since different methodological or architectural choices will yield different results. The third challenge corresponds to the evaluation process. There are many metrics used to assess the quality of a fault reconstruction approach, and sometimes they can yield contradicting results. With all this in mind, we designed a comprehensive benchmark study composed of three main steps. A pre-training step, where a model acquires knowledge from a source domain. A fine-tuning step where a model tries to adapt this knowledge to a target domain, usually by updating its final layers. And an evaluation step, where the fine-tuned models are tested across multiple datasets and metrics to assess their robustness. This three-step process composes our experimental setup. We also used 3 datasets in total for our experiments, one of which is our recently introduced CRACS datasets, including multiple sets of crowdsourced annotations, which allows us to further divide it into 3 datasets for training and fine-tuning. We also evaluate 8 models in total, spanning large transformer models like SegFormer and smaller ones like UNIT and RCF. Overall, this leads to over 200 exhaustive combinations of experimental setups. Now, as I mentioned before, we used 3 datasets for our experiments. The FaultSeg 3D dataset is a common synthetic dataset, and the crowdsourced CRACS dataset based on the F3 block and Thebe dataset, both of which are common real seismic volumes. These make our benchmark highly heterogeneous. As we showcase here, through a UMAP embedding of frequency descriptors of each dataset on the left and a radar plot of characteristic metrics on the right. This tells us that both at the data and the label level, there's a non-trivial degree of shift between our datasets. Now, one of the prevalent issues we find across our experiments is catastrophic forgetting. For instance, given a model trained on cracks, it learns to recognize the patterns in this dataset and does well at detecting the faults within it. However, when this model is then fine-tuned on FaultSeg 3D, the information from the source domain is lost, and its performance on cracks degrades. Ideally, we want a model to operate in this blue region, where information on both source and target domains is kept. We find in our study that methods like elastic weight consolidation, or EWC, achieve this region, but only when the shift between the source and the target is not too big. Then there is the issue of domain shift. In some cases, no amount of pre-training or fine-tuning is enough to get good performance when the degree of the shift is too large, as is the case in the Thebe dataset. In this case, domain adaptation methods like DANN or FDA are able to allow models to better harness knowledge from the source data and achieve good performance on the target data. However, we observe that these methods only work when the degree of the shift is large. Finally, we also introduce a qualitative analysis based on a number of fault-oriented metrics like length, curvature, and density, which allows us to understand the structural interplay between the properties of the seismic data and the architectures used.